The term, RMS, is an acronym for root mean squared. RMS defines the power that an AC source produces. In order to understand the definition of RMS, and what an RMS voltage is, we must first identify the basic differences between DC and AC voltages. A DC power source, like the battery shown here, creates electrical current in only one direction. An AC power source, such as a typical 120-volt receptacle, creates an alternating current. The current flows in one direction, stops, and then creates current in the opposite direction. To understand the term RMS, let's first examine how an AC voltage is created. A magnet has invisible lines of force called flux. These flux lines are strong at the poles and weak away from the poles. When a conductor is moved through a magnetic field, current is created in a circuit. In the example shown, a conductor, connected to a circuit, moves through a magnetic field cutting the flux lines. The result is current flow in the circuit. The current becomes stronger as it moves through dense flux lines and weaker as it moves through less dense flux lines. When the coil moves in the opposite direction, the direction of the current reverses. In this example, the magnet rotates, creating a current in the circuit. Notice in the example shown here, that the current flows in one direction during the first half of the rotation and in the opposite direction on the second half of the rotation. One complete rotation produces a voltage in the circuit that starts at 0 volts, goes to a maximum voltage, returns to 0 volts, and goes to a maximum voltage in the opposite polarity. Let's take a closer look at the voltage that is created. Notice in the example, the rotation of the magnet creates an alternating voltage. The voltage starts at 0, reaches a maximum voltage, returns to 0, reaches a maximum voltage in the opposite polarity, and returns to 0. This alternating voltage is AC. AC voltage is constantly changing in magnitude and polarity. In this example, the maximum voltages are 10 volts positive and 10 volts negative. The term, hertz, or cycles per second, indicates the number of revolutions that the magnet completes in 1 second. 60 cycles per second is the standard in the United States. This means the magnet rotates 60 times in 1 second. An AC voltage continuously changes in magnitude and polarity. To get a clear image of the changing AC voltage, let's examine a graph of the voltage by drawing the relationship between the voltage and the time that it takes to produce the voltage. In a graph of an AC voltage, the horizontal values represent time while the vertical values represent the voltage produced at that time. The beginning point of the drawing begins at 0 volts and at 0 time. As AC voltages produce over time, the voltage rises to a peak value, goes back to 0 volts, rises to a peak value in the opposite polarity, and once again falls back to 0 volts. The result is a drawing of one complete cycle of an AC source. This drawing is called a sine wave. A sine wave is a drawing of the time-voltage relationship of an AC voltage. Ohm's law consists of math formulas that use voltage, current, resistance, and wattage values for circuit design and troubleshooting. Ohm's law formulas use two known electrical values to find an unknown electrical value. Notice in the Ohm's law formulas shown here, that a voltage value is used. A voltage value must be known. What is the voltage value used in the formulas? A DC power source typically produces a constant, unchanging voltage value. In a DC circuit, the voltage value used in an Ohm's law formula is simply the value of the DC voltage source. However, an AC voltage source is constantly changing in magnitude and polarity. Remember, an AC source produces a range of voltages from 0 to a maximum voltage. So the question is, what AC voltage value is used in Ohm's law? And, what is the electrical work that a constantly changing voltage produces? Let's examine how this is determined. Root mean square, or RMS, is a mathematical formula that determines the average electrical work produced by an AC sine wave. The formula basically uses voltage points of a sine wave to solve the equation, root mean square. The result of the equation is an average electrical value of an AC voltage, or the average electrical work of an AC voltage. The RMS voltage value is used in Ohm's law formulas. Let's examine the RMS value and how it compares to the peak voltage of a sine wave. To identify the relationship between the peak voltage value and the RMS voltage value, half of the sine wave will be examined. Since the RMS value is an electrical average, the RMS value will always be less than the peak voltage value. Notice in the example shown here that the RMS value is less than the peak value. An RMS value can be determined when the peak value is known. The peak value is multiplied by 0.707 to solve for an RMS value. The peak value can be solved if the RMS value is known. The RMS value is multiplied by 1.414 to solve for the peak value. Remember that an AC voltage continuously changes in magnitude and polarity. The RMS value of an AC voltage is the amount of electrical work that is produced. The RMS value, not the peak value, is used in Ohm's law formulas. Let's examine the value displayed on a voltmeter. A typical multimeter has various settings. One of the settings is used to measure AC voltage. The AC setting on a meter is typically identified with a sine wave or the letters V, A, C. In the example, the meter is set to AC and is used to measure the voltage of the 120-volt receptacle. The value displayed is an RMS value. It is important to note that the sine wave peaks at about 170 volts. However, an AC meter will display an RMS value. To understand what is meant by true RMS, let's examine a variable frequency drive. A variable frequency drive, or VFD, manipulates a sine wave in order to control the speed of an induction motor. The VFD is capable of changing the amplitude of the output, that is, the height of the sine wave. The VFD is also capable of changing the frequency of the output, that is, the number of cycles occurring. However, a typical VFD not only changes the amplitude and frequency, but can produce pulses that simulate the shape of a sine wave. The output of the VFD creates variable speed capability for an induction motor. Let's examine the effect of these on a voltmeter. A standard voltmeter will display the proper RMS value of a typical sine wave. These meters are adequate for most applications. However, many voltmeters are not designed to display correct RMS values for changes in frequency or amplitude. These meters are also not designed to display a true RMS value for AC pulses created by variable frequency drives. Meters designated with true RMS are designed to display a true RMS value no matter the shape or size of the sine wave. Meters that are capable of measuring true RMS are usually identified on the meter and in the meter specifications. Knowing the difference between the two types of meters can be beneficial for circuit design and troubleshooting.